So hello everyone, welcome back to our seminar. Today we have Joe Leja. He's an associate professor of astronomy and astrophysics at the Penn University and holds a mid-career endowed faculty chair. He studies how galaxies like the Milky Way form over cosmic time using telescopes, large surveys, and supercomputers. His work focuses on modeling distant galaxies and data-intensive astrophysics, including tools like prospector. He earned his PhD from Yale in 2016 and was an NSF postdoc at Harvard's Smithsonian and has been named a Clarivate highly cited researcher in 2023 to 2025. So I'll give you the floor.
Cool. All right.
Start whenever.
Oh, just let me know when it's good to start.
Yeah, you can start.
Excellent. Thank you. Well, thanks for the lovely introduction and great to visit even virtually. Hopefully someday I'll be able to make it out in person. But hey, I spend most of my time thinking about how galaxies evolve. And so I think the James Webb Space Telescope has been amazing and has generated lots of problems, some of which I'll touch on today as motivation. But I think in addition to this breathless science at the edge of the observable universe, I work a lot on these new kind of data-intensive methodologies. And that's what I'm going to focus on more today. I think we're still learning how to use machine learning effectively, especially in the subfield of galaxy evolution, which tends to be more observationally driven. But my group spends a lot of time building these next generation modeling tools, and it's going to completely change the way we do observational galaxy science. I think over a short time scale, maybe over the next 18 months. I used to say over the next 5 years, but that timeline has really shortened a lot, in my opinion, thanks to the ongoing exponential growth of large language models that make this type of work much more accessible. And I don't think anyone is prepared for this, really. Modeling that required 1 million core hours on Harvard's brand new supercluster 10 years ago. Hey, work that I did, very intensive, very expensive. Now one of my grad students can do it in 20 minutes on a laptop. That's a factor of 2.5 million speed up in 10 years. Transformational. And I think the speed increases are perhaps the most boring part. I think the exciting part is the new types of science we can do once we're no longer worried about speed or computational efficiency so much. And I think this kind of revolution is going to make the 2020s the era of complex, sophisticated modeling. It's going to be completely different. So let me tell you about it. There we go. Good. So just a quick reminder of what I'm thinking about here. So when I say galaxy SED modeling, what I mean is fitting these observed spectral energy distributions. So this here is a beautiful galaxy, Andromeda, observed from the radio to the X-ray, and then building forward models that transforms these beautiful images into, of course, similarly beautiful inferred parameters. Hey, things like the stellar mass in a galaxy, the star formation history of a galaxy from its stellar populations, the nebular properties and the nebular physics in that galaxy, the dust contents, the chemical abundances of the gas and the stars, and maybe any active black holes, particularly supermassive black holes. These are the things we're trying to learn from galaxy data or surveys of the distant universe. And so I'll focus mostly on the process of turning these data into science, into information today. And so I'll just start out by establishing a few basics, things that we always think about when doing this type of modeling. And one is that stellar populations in distant galaxies are almost always unresolved, i.e., you can't see any individual star. You have to kind of model the sum of the light. And so here on the left, we see Andromeda. Spans many full moons on the sky in all of its glorious detail. You can pick out many individual stars. You can do very detailed color magnitude diagram modeling like this, but we don't have that luxury for most distant galaxies. Hey, on the right, this is more like what we get with a typical distant galaxy. Maybe you can tell it's got a disk of some sort and a bulge, and then as you go into redder and redder data, you really lose that information. And so this is one of the core challenges of modeling distant galaxies is that we have to model the sum of the light. And that means we are always subject to outshining. So bright young stars, giant stars, these all tend to dominate the light budget no matter what part of the electromagnetic spectrum you're looking at, and they will completely obscure other things that may be more scientifically interesting for some purposes. So outshining is an eternal problem. But, thanks to many decades of investment in these deep surveys of the distant universe, our modern surveys tend to be quite data rich. Often modern galaxy evolution surveys are multi-wavelength with imaging or photometry at tens of wavelengths. Here's an example from one of the deep extragalactic fields. This will often let us span the rest ultraviolet through the rest near infrared for distant galaxies, um, even out to very high redshifts nowadays. And so this is very useful. We live in a data-rich environment. And similarly, you can tell a similar story about spectroscopy. It's more expensive, so it tends to be a bit more rare, but I think that's also changing with these large-scale multiplex ground-based surveys coming online. I'll talk more about this later. Right, but with spectroscopy, you can get some very information-rich data here. This is a Webb spectrum of a distant quiescent galaxy. I'll come back to it in a little bit. But you can see it has a rich pattern of absorption and in some cases emission lines that can tell us a lot of information about things like the star formation history of a galaxy or the elemental abundances in a galaxy. Um, so these are information dense, lots of pixels. Can we model all the physics that goes into them? And if we're lucky, we can sometimes get both types of data. We can have both a wide baseline of photometry and detailed spectroscopy. In that case, we can learn a lot by modeling these things jointly. We can get mass and dust constraints from the photometry, and from spectroscopy, we can get star formation history and metallicity constraints. This is the most interesting types of modeling, I think, for reasons that I'll explain shortly. You can break a lot of the degeneracies here. So this is the type of data I'm thinking about. I'll spend a few words talking about the models I'm thinking about. First, I think Bayesian modeling is often very helpful for interpreting galaxy data. And I have a specific motivation for this. This is because when we're thinking about distant galaxies, we often have tens of parameters that we're interested in learning. Things about the star formation history, the dust content, the abundance pattern, the black hole activity, and so on. And at the same time, all we really get is a spectrum and photometry, usually of the integrated galaxy. And so that means, in Bayesian modeling, we're kind of in the sweet spot for Bayesian modeling, where both our data are informative, they're telling us something, but our prior also models, our prior also matters. The way we think about our data and our prior assumptions about the physics that go into it is quite important. Hey, there are different types of these problems. You can have a data-dominated problem. That's a situation where your modeling maybe isn't so important. The data tell you the answer quite clearly, and you could have a prior-dominated problem where your data tell you absolutely nothing, and we leave those for the theorists. But distant galaxies tend to sit in this sweet spot right in between the two, where you really need to think about both. And so it's often helpful to set this up in a Bayesian way. Okay? Both these things matter. And so here, this is just a little movie using Prospector. This is an open source Galaxy SED fitting code that I've helped to develop alongside Ben Johnson. It's been out for a long time now, and so this is just a little experiment where we start with a simulated galaxy that we observe in one band of photometry, and we fit some 16, 18 parameters to that band. And then as the movie marches on, we add in an optical color, 5 bands of optical photometry. We go into the rest near infrared and the rest UV and then the rest far infrared. And we add more and more information. And so I don't want you to pay too much attention to what's going on the right. We're learning a bunch of things about a bunch of different parameters. But what I want you to take away from this movie is that We can build very complex models, and we can happily fit them to small amounts of data, and we can still get very sensible answers. It's totally fine to have 20 things you want to learn about a galaxy and one data point to fit them to. You won't learn very much, but you won't be wrong. And so the universe can be arbitrarily complex. It can be as complicated as you like it to be. All we have to do to understand it, or at least all we have to do to attempt to understand it in a principled way, is to simulate the right physics and attach those to the observations, and then we can marginalize over that complexity and learn the stuff we want to learn. Sounds easy in practice, maybe. Um, but this works as long as we know all of the important physics and we can write them down and put them in our models. Are we there yet with distant galaxies? And now this is where I say, sort of. Uh, So Bayesian inference, I think it's powerful, but it's dangerous. You can do a lot with it, but you often can be mistaken into thinking you've learned something if you're not careful. We don't always learn the right things. And so this is an old saying, and I like to say it all the time because it's always important to keep in mind all these models are wrong. In detail, every model is wrong, but some of them are useful. Uh, What do I mean by useful? It means we create new knowledge. We learn something new about the universe. We learn something we didn't know before. So that's our goal. That's everyone's goal. We're scientists here. But first, to get to this new piece of information, we have to understand a lot. We have to be sitting on a solid foundation. Okay? So we have to understand our data, our measurement uncertainties, our instrumental effects, our sky emission, and so on. Okay? We also have to have reasonably accurate generative models for what we're fitting. So we need to understand what physics we're putting in and why, and make sure that those physics that we're putting in correspond to what's actually happening in the universe. Right? Both these things have to be true in order for this to be useful. And if this is not true, careful. Hey, modeling can do a lot more harm than good. And so I've heard an analogy that I quite like. Simple models are like a little paring knife. You can get a lot done. They're simple, useful, versatile tools. You can use them in a lot of situations. But when we start scaling up, when we have a lot more work to do, hey, we want to build a much more complex model, and that's more like operating a chainsaw. It's very powerful. You can get a lot done with it, but if you're not careful, you might chop your arm off. And so, as our models get more complicated, we need to also be more careful and know exactly what we're trying to measure and why it's important and why it's capable. So, are we there yet? Are our models accurate enough to be useful? The answer is sometimes. So I'll just walk through a quick of the surprises from Webb, a quick tour of some of the surprises from Webb. Okay. So one of the first things that came out of the James Webb Space Telescope's observations of the early universe. Every time we turn on a new telescope going farther in the infrared, we always expect there to be no quiescent galaxies, and we're always surprised when the universe continues to produce large quiescent galaxies early on, galaxies that have shut off their star formation, perhaps permanently. And this has happened again with Webb, but with a new twist. This here is a spectrum of a galaxy at redshift 4.9. The universe was about a gig year old. This is from the Rubies survey, and it has a gigantic Balmer break. This feature from dense, warm hydrogen in stellar atmospheres. Classic sign of old stars. Okay. This object is also very small. It's something like 500 parsec radius, while being about 4 times as massive as the Milky Way. So this is a very, very dense, very, very old object near the beginning of time. That's not why it was surprising. Why it was surprising is when we try to model the formation history of this galaxy. This is a quiescent galaxy that we are modeling in the rest frame optical. This is where our models should work the best studied regime using the simplest stars. If we try to model these data, we get formation histories that look like this. Here, the y-axis is the total amount of mass formed in this galaxy. The x-axis is the age of the universe. And here I'm plotting two different formation histories from modeling this galaxy with two different sets of assumptions. Okay. The light blue model here, this is if you assume a solar metallicity. The data aren't quite good enough to constrain metallicity on their own. If you assume a solar metallicity, you get a very rapid formation. Not illegally rapid, but very rapid. Right, and so here there are two lines drawn on this plot, epsilon of zero point 0.2 and 1. Epsilon of 1 means every baryon in your halo has turned into stars. Epsilon of 0.2 means 20%. And so, for reference, in the Milky Way, after about 13.7 billion years of turning gas into stars, we've turned about 5% of our baryons into stars. Okay? This galaxy has either turned 20% of its baryons into stars, or, more worryingly, the best fitting model is in purple. Okay? Here we turn not just 100% of our baryons into stars, but more than 100%. Okay? That is, well, it's not illegal in Lambda CDM, but it's pretty uncomfortable. Even the easier late forming solution is quite uncomfortable. Okay? And you might look at this and say, preposterous, you've done something wrong. And that's what we said the first 20 times we did this modeling. But this has been an emerging consensus. There are many independent studies, many independent observations that are coming to similar conclusions. There are multiple ultramassive dead galaxies in the very early universe that seem to have formed and died in the first 500, 700 million years, and they seem to have converted more than their halo's share of baryons into stars, or at least 50% of their baryons into stars. One of these is probably illegal in Lambda CDM. The other is just very, very uncomfortable. So, what's going on? Are our models wrong? Is the data wrong? Are we interpreting these wrong somehow? We don't know yet. I have a few ideas, but this result doesn't seem to be going away, and I think we need to grapple with it carefully. This has been a lot of fun to think about. So this is an ongoing mystery from Webb. Webb has been a fantastic instrument and has revealed a bunch of other surprises, many of which are challenging to our normal models. Here's another one. Hey, there are a lot of galaxies, something like 100 plus and counting now, where we've identified in the rest UV spectrum, not just a, normally we see a Balmer break when you have a lot of old stars. If you have a lot of ionizing photons, you can excite gas into creating the inverse of a Balmer break, a Balmer jump, right? A nebular dominated system. You can see these normally in the local universe. If you take a spectrum of a pure H2 region, you'll see this nebular emission popping up. But now, at higher redshifts, at redshift 4, 5, 6, 7, 8, we're seeing galaxies that seem to be functioning as an entire H2 region. Okay, so these are nebular dominated galaxies, which is wild to think about. This is difficult, maybe impossible to explain with normal stars. You need these incredibly high ionizing photon production rates. You need very, very steep UV and far UV spectra. And so the only way you can really get there with normal stars is by playing with the initial mass function. You can get there other ways, though. If you can have ubiquitous hidden AGN, we might need to start tinkering with our stellar models. We might need to think about population 3 stars, okay? I'm not saying any of these are definitely what's going on. We don't know what's going on. But a lot of these have been identified now, and we need to think carefully about our standard models because we just can't make these with normal stellar populations. And we need to start breaking the mold here. One more mystery I'll talk about briefly that we found in the early universe. We are used to finding low mass galaxies, things like the Large and Small Magellanic Clouds, being nearly 100% star forming. The only way we can turn these things off is by putting them in a very dense cluster environment, and these very dense cluster environments just don't exist in the early universe. So it was a huge surprise when Webb turned on and we started finding these low mass galaxies that seem to be dead. They seem to be turned off. They have these small Balmer breaks. This implies that star formation has stopped for tens of millions of years. The explanation that has emerged and has grown is that these galaxies are experiencing very bursty star formation. They have a sharp burst of star formation that produces so much feedback that they turn off for some tens of millions of years, and then gas reaccretes and they begin star formation again. That's been the emerging hypothesis. Hey, there's still a lot of physics questions about them. What are their duty cycles? What are the time scales of these systems? It's very sensitive to the feedback models in the early universe. This is an opportunity to learn what those feedback models are in great detail. Hey, this seems like a great problem for galaxy SED modeling. Hey, we can solve this by modeling these SEDs very carefully and getting the up and down fluctuations in detail. Right? I'll come back to this later, but I'll just say now, this is a very, very, very hard modeling problem, and it's proved to be somewhat pathological. So, due again to the outshining issue. It's very hard to get good formation histories for these objects. I'll tell you how we think we can do it later on. Um, but the point is, James Webb at this point has presented us with many different exciting problems in galaxy formation, and they're big problems too. These are not small. These are factor of 10 issues. And so many of these need to be solved by modeling the data better. But I think the models still have a fair way to go. Let me show you why. Um, Here, this is a galaxy SED fitting experiment. This was conducted by Camilla Pacifici from Space Telescope Science Institute a few years ago. This was a fantastic study. And so what she did was she got together some 13 different groups, 13 different research groups all around the world who build these kind of SED modeling codes. And they took all of these popular but different SED modeling codes, and then she applied them to, or she had us apply them to, this identical, very high quality REST UV to near infrared space-based photometry. It's exquisite. It's from Hubble. It's very well vetted of very normal galaxies. And all she did was say, hey, run these through your code and give back whatever you get. Um, and so this was a fantastic study. It was an exercise a bit in diplomacy, getting 13 people to all run their code and report their results fairly, and we found a few bugs along the way. But this was one way to look at the results. So here, these are 13 different boxes representing 13 different research teams all around the world. And all they're doing is showing the so-called galaxy star forming sequence, the relationship between the mass and the star formation rate of each galaxy. Okay. The color coding, you don't need to worry about it. It's how much dust is in each galaxy, but it's not too important for this purpose. All I want you to do is look at how different these galaxy populations are. The line in each panel is just to guide the eye. It's the same line in every panel. And so if you look at this in detail, you'll notice that galaxies that live on the star forming sequence, this main cluster of points, okay, that sequence moves up and down by quite a bit. Keep in mind the y-axis is about 4 orders of magnitude, so small motions are very, very consequential here. So the star-forming sequence moves down a lot, up and down between codes, regardless of the data. No change in data at all. The amount of scatter around that star-forming sequence is dramatically different. So for example, P12, which is in the lower right area, this is Cammie's code. She finds a very, very tight star forming sequence. But something like Prospector in the lower left finds a huge amount of scatter in the star forming sequence. And, and also, the picture of dead galaxies, the galaxies that are far below the star forming sequence, is different in every code. Some of them seem to have a wide range of star formation rates. Some of them are pretty close to the star forming sequence. Some of them are very far away from the star forming sequence. And then the so-called Green Valley, the area between the star forming sequence and the dead sequence. Some codes have this. Some codes it's very well populated in. In other codes, it's a complete desert. There's nothing there. Right? Why? Why do we all disagree so much? Hey, what's going on? And I'll tell you, we found a few bugs in this exercise, but the results you're seeing here are not due to bugs. These are smart people making good choices. They just tend to be different choices, and they give different results. So what's going on? Okay. Fine. You might say, well, Joel, photometry is very hard. There's a lot of degenerate solutions in photometry. I don't think this is a good test. Okay, fine. Forget about photometry. Let's talk about modeling the best spectra of distant galaxies I've ever seen. Okay, incredibly good spectra. This is from the Legacy survey, PI Arjen van der Waal. And so this is some 20-hour rest optical spectra on an 8-meter telescope. This took something like 5 years to assemble, was enormously expensive. And we have these spectra with, R of 3500. This is very high for galaxy evolution. And cellular noise per angstrom of 20 to 70. You're never going to get better spectra for galaxies in the distant universe. I mean, This is about as good as it gets. Hey, these are beautiful spectra, and here's an example of a couple fits to these spectra. You see all of these emission and absorption lines in exquisite detail. Hey, fine. Let's do the same exercise for the best data we'll ever really get in this field. And, this is a bit tougher. Here I'm only going to show you the comparison between three different codes, prospector, bagpipes, and this lick index fitting code, a Basta from Galazzi in Italy. And so here I'm showing you on the left is the inferred metallicity between prospector and Basta. And on the right is the inferred metallicity between bagpipes and prospector. There's no relationship between the X and Y axes here. None at all. Right? The scatter looks okay because we have a small parameter space, but basically we don't agree on this. We don't even agree on the quiescent galaxies. And, and here's an example of the same comparison for light-weighted ages. This is supposed to be a more robust measurement as compared to the mass-weighted age. It's basically what is the age of the light that we're observing with our telescope. This looks a bit better. It has to, I think, by construction, but it's also pretty dang bad. Eh, So even with these excellent spectra, we're still not getting very good agreement between codes. Zero agreement on metallicity. I have a few ideas about this, but not solved yet. And quite poor agreement on the ages. So why? What's going on? Hey, why can't we agree on these things? I'll tell you my hypothesis here. I, I think the challenge is that galaxies are enormously complicated systems. They're ecosystems. There's so much going on. There's many different types of physics in play. And in order to put all these compacted into a model that's fast enough to run, you need to make a lot of approximations or assumptions. And those assumptions create systematic uncertainties on their own. Okay. I'll just show you an example of this. So I'm just going to play a little movie. On the left, you'll see some parameter that affects a galaxy's SED, and on the right, you'll see some approximate order of magnitude effect. How much does it affect the SED? And I'll just let this movie play, and you can watch. So there's a lot going on, and I truncated this movie a little bit early, but I'll point out that you could keep going. You can name things like cosmic rays, magnetic fields, and so on, X-ray binaries. But some of these parameters also, like the stellar abundance pattern, in principle, that's tens of parameters on its own. Okay. So the point is, we have a lot of stuff we need to know, and our data don't tell us that much information. So how do we move forward here? What's the next step? Uh, I think the answer is we need to add more physics to our models. But you immediately run into a problem here. High dimensional models, we're already hitting our computational limits. You can't just save a high dimensional model to your computer storage. You can't live on a grid. You run into this curse of dimensionality where you would need basically a whole Google data center to store a 15 parameter stellar model. So that means you kind of have to run everything on the fly. You have to generate things on the fly. And that's just a compute intensive task. It takes somewhere between several hours to tens of hours to run a fit, or several million hours to analyze a big, large, deep extragalactic field. Why is it so slow? What takes so long? I'll just show you briefly what we do. We take our galaxy observations, we feed them through some physics model. We can generate a fake galaxy. Here, this is using Charlie Conway's flexible stellar population synthesis model, but we can generate a fake galaxy full of stars, black holes, dust, gas, and so on. We spent a lot of time optimizing this. We can generate about 20 models per second. Sounds pretty good, right? 20 models per second. That's not bad. There's a lot of complex physics that go into this. Well, in this case, it takes about 1 million models to fit a distant galaxy. And so you can do the multiplication yourself. You end up somewhere around 15 hours per object. And you can slice a bit at this. You can chunk out some factors of 2. But the basic fact is, this is slow. So what do we do? How do we speed things up? Well, first thing we can do is just replace all of those carefully curated physics with a so-called neural net emulator. And so a neural net emulator, this can reduce our model generation time by factors of 100 to 1,000, depending on how loose you want to get away with this, or 10,000 on a GPU. I'll walk you a bit through how it works and what the drawbacks and advantages are of this approach. But basically what we say is all these complicated physics calculations that take a while to do, we'll just learn the relationship between the inputs and the outputs and then put it into a neural net. And so basically what we're doing is we're trading accuracy for speed. Okay? And so we thought a lot about this. As you make your emulator larger, you can get more accurate approximations, but you lose speed. And so there's some trade-off. You want your neural net to be small, so you get a lot of speed train up or speed ups, but you also want it to be accurate enough to do science. And so you have to think a bit about this trade-off. And so here's just an example. We trained many, many neural networks in this exercise, led by one of my students, Leja Matthews. And we found, running many, many different fits, that the rule of thumb is your emulator should add something like half of your observational uncertainty or less. So if you have solenoids of 20 photometry, you probably have an error budget from an emulator of 1 to 2%, more or less. That's the magic number. Your emulators need to be about twice as good as your observations. Um, Once you put everything into an emulator, you get some other advantages as well, though. One of the things you get is automatic differentiation. Right? This is how machine learning algorithms can learn millions of parameters, right, through this automatic differentiation. That means you get the gradient out of these codes for free. Um, and this is another advantage of an emulator. This lets you use fancy gradient-based samplers or other ways to fit your likelihood space that are super efficient. And this is just an example. So normally what we do is we have some random walk sampler that will use some heuristics to guess at where it should go next based on where it is. And that's a very flexible, adaptable model, and given enough time, this random walk will eventually get you to your true solution. If you have gradients, you can do something much more efficient. You can measure the slope of the likelihood surface at every location. And so gradients let you do something more like this. They head right to the truth, assuming you have a well-behaved likelihood space. And so this gradient-based sampling is just very efficient at proposing efficient, good samples. And then finally, most important for scientists, emulators can yield accurate inferred parameters. So if you choose the size of your network right, you tune everything properly. Here, this is just an example of fitting some mock data where we're able to recover the true mass and the true amount of dust in a galaxy to high precision. And we're able to get good answers out of these emulators. Okay. So let me just show you an example of using some of these in practice. One of James Webb's first deep extragalactic fields uncover. We spent a lot of time working in this field, found a bunch of very cool stuff here. But my research group did the modeling for this survey, and we found we could fit some 70,000 galaxies in one of Webb's first deep fields on a couple of days on a modest compute allocation. So we were able to do real good science with this. And distances or redshifts that we inferred from this modeling with a neural net emulator, all of our physics has been abstracted away, they were excellent. Actually, in some cases, they were better because we have these smooth models. And so we were able to find the second and the fourth most distant galaxies at the time using these emulators. And we found them in this very deep field, redshift 12.4 and redshift 13.1, which was stunningly fun. Very, very cool. And one other advantage of these emulators is because they work so fast, you can do rapid turnaround on the modeling side. It only takes us a couple days to do this work, so we can analyze the data right when they come in. Okay. So this is great. I'll show you briefly one example of taking this to the next step. Something called simulation-based inference, which is rapidly becoming the coolest inference technique in the field. So this is work led by a grad student in my group, Lishan Shi. She's in statistics, actually. But here you take it one step further, and you don't run any inference at all. You just go straight from your noisy observations to your answer. And so Here, I'm just showing a little movie of Lishan running simulation-based inference on the bottom compared to our normal, standard, slow, nested sampling approach on the top. Hey, in her case, she's able to get a good answer for this nested sampling fit after about 2 days of thinking. In the same time, on the bottom, you can fit something like 2.5 million galaxies with simulation-based inference. Hey, that's how stunningly fast it is. You can watch the terminal spitting out answers at you. Every 0.02 seconds, you get a new fit. It's amazing. Hey, this is the factor of 2.5 million speed up I alluded to at the start of the talk. This is how you get there, and it works remarkably well, like way better than I would have expected it to. So this has been so much fun. Um, and so hopefully I've convinced you we can do all the same things that we've done in the past, and we can do them way, way faster and way more efficiently. But that's actually maybe the most boring part. Because we can also do completely new types of science. If our models are 2.5 million times faster, what else can we do that we haven't even attempted to do in the past? And so I'll walk you through a few of the sort of new age, new types of science that we can do with these ultra fast models. Things like forward modeling imaging. You can fit hundreds or thousands of pixels simultaneously, all at the same time, each with its own complicated physical model. And all of these fits are correlated by the point spread function, so you have to fit them all at the same time. I'll show an example of that. It's been a lot of fun. Okay. Or you can do so-called population modeling. Instead of fitting galaxies one at a time, you could fit thousands of galaxies at the same time. You can treat them as part of a cohesive galaxy population, and you can learn completely orthogonal pieces of science from this. This is how I think we can solve the burstiness problem, and I'll show an example of this later on. Okay? And ultimately, I think the sort of 5 or 10 year goal is that galaxies are cosmic ecosystems. They're the only example we have in many situations of types of exotic physics or stellar evolution phases or new types of black holes that we can only see in the distant universe. And so I think the ultimate goal is to be able to build these tools that can learn, or maybe just marginalize over, all of the relevant physics that we care about. We already have models of accreting supermassive black holes or models of chemical evolution, stellar evolution, photoionization. All of these on their own are rich, complex fields of inference. There already exist models with hundreds of parameters that are well calibrated and well thought out. All we need to do nowadays is hook these right up to an inference package, and we can learn all sorts of things about the universe that we simply couldn't do 5 years ago. And so I think this field is changing very, very rapidly, for reasons that, both advances in computation and advances in abilities people to use this computation, thanks to large language models, they're opening up completely new science directions. I'll tell you about a few of them for the rest of the talk here. So remember at the beginning, I said, remember, we treat stellar populations in distant galaxies as unresolved. But they aren't really, right? If you look at this galaxy, you can see some features. You don't need to draw a little circle around it and add up all the flux. You can model everything as you are. And so fitting every pixel has these key advantages. If you fit the data as they are, you remove a lot of intermediate layers of analysis that create these tough systematics. And you can also use a lot more information. You can break these degeneracies. You can measure things that you care about much more precisely. Mass, age, star formation rate, at least 2 to 3 times more precisely, in some cases a lot more precisely. This has always been a challenge, though, because the key challenge here is that the pixels are not independent. They're all correlated via the point spread function. Hey, they all know about each other. They've talked to each other in the past. So if you want to do this properly, you can't model every pixel independently. You have to model everything at the same time. You have to build a model of the galaxy, smear it by the point spread function, then compare it to the data. Okay, so modeling simultaneously thousands of pixels at the same time, that used to be a fantasy. 5 years ago, that was impossible. Okay. We can do it now, and we can do it quite efficiently. So I'll show you an example of some of this work. You can forward model stellar populations and the point spread function. And in this way, you can model photometry of any resolution. You can do it all at the same time. You just build a model in model space, and then you smear every image by its own point spread function and add its own pixelization. But you don't need to do anything to the data. You fit them as they are. Everything complicated happens in model space. Currently, we're just treating every pixel like another galaxy in the sense that we fit it with all its own unique metallicity, dust, star formation history, and so on. I'll touch on why this is complicated in a couple slides. Okay. These neural net emulators, they give free gradients, and these power just these hyper-efficient sampling methods, which I won't get into at all here. But in brief, fitting a 75 by 75 pixel image with 20 bands of photometry, you can do this fit in about 30 minutes. Just to be clear, okay, this is something like 84,000 free parameters. Okay? And in mock data, we can show that we get out what we put in. This is a new era of modeling, and it's so much fun to do. Uh, Classically, this kind of fit would take something like 100,000 core hours. But I apologize. I'm working from home today, and my dogs are being a bit loud. Give me 1 second. Oh, apologies. I hope that wasn't too disruptive. Um, but classically, this would take something like 100,000 core hours. So we're something like 500,000 or 5,000, 50,000 times faster. And we can maybe potentially get the right answer. So this has been so much fun. So how does it work? What does it look like? Uh, so we've started playing around with the data here. We can fit these beautifully spatially complex galaxies from, in this case, a Webb Deep Field, the Minerva survey. Okay, and we get these spatially complex systems. Here's just an example of the mass and the metallicity gradients we get. And we can see that there's a lot going on in these systems, and we can learn a lot more by modeling the data as they are. Okay, they're rich, they're complex, they're sophisticated. There's a lot of gradients going on, and simply fitting all the same properties to this one galaxy wasn't maybe a good idea in the first place. Okay. Just an example of this, we get much better constraints on the stuff we want to know. In this case, the stellar mass. Right? So typically we have a 20% uncertainty on the stellar mass, 20, 50%. Tests on mock data suggest we're getting uncertainties of 5%. And these are well calibrated. They're correct. Okay? So this has been just a super exciting project, but we're not really done yet. There are some complications. Okay? So there's a key challenge before just deploying this on the whole sky. More pixels, more problems. Okay? So here's an example on the left. We're fitting, in this case, we're just changing our priors about how the small scale variation of dust, age, and metallicity is correlated. So how much do the pixels know about each other? How much do the stellar populations mix? How much does the dust mix? And so on. And so just tiny little changes to how we think galaxies might be structured on small scales. And then on the right, I'm just showing you the recovered log mass, the recovered stellar mass from these very different small assumptions. And if you can read the numbers here, we're getting a difference of about zero point 0.6, zero point 0.7 dex here. So factor of 6, 5 or 6 difference in the recovered stellar mass. But all of these fit the light perfectly. They all produce the same galaxy. And so I think we're entering a new regime of degeneracies when we're doing this type of spatially resolved modeling. The point spread function smearing allows many different types of solutions. And so before we kind of run out and do every sort of fitting that we can do, fit all these things in 10 or 20 or 30 minutes on a GPU, I think we need to be really careful about understanding our dynamical mixing of stellar populations of different age metallicities, dusts. And so I think starting on local galaxies is the right thing to do with these types of models. Otherwise, we have a lot of things that we don't know that affect our answers. And so work is ongoing. There might be simple solutions to this, but the takeaway is that spatial resolution alone isn't enough. We need a bit more, maybe spectroscopy. Eh, Fine. So that's one thing we can do that's new. Let me tell you about another thing. Star forming regions, stuff we know about, nebular modeling. So normally a star-forming region is a large region of hot and cold gas ionized by these bright young stars. Here's an example of our own galaxy, the Eagle Nebula. And these regions are complex. They have complex physics. We use codes, photoionization codes to model these, something like cloudy or mappings. These have hundreds of parameters and take several minutes to run for any given configuration. But they are fantastic pieces of physics. They're the best way to count young stars, by understanding the emission lines from galaxies. They're the best way to understand the growth of galaxies, at least their most recent growth rates, by understanding their nebular evolution. And so we played a similar game with these photoionization models. And so here I'm going to tell you about a code named Q, where we build a fast and flexible neural net emulator for Cloudy. And so it's the same game. And we put in some parameters that we want to learn, and out come some observations. And so instead of running Cloudy, we just have a neural net emulator that takes the place of Cloudy. Okay. And so in this case, what we can do, the way we ran it, is that we put in a power law ionizing spectrum to the to Cloudy. We ran Cloudy many, many different times. And so afterwards, we trained our neural nets on this pair, the input power law or segmented power law, a four-part piecewise continuous power law modeling the ionizing spectrum. And then we learned to put in that power law and get out predictions for line luminosities. And so the outcome is that we're no longer tied to specific models of ionizing continuum from stars or from AGN or from whatnot. We can learn what the ionizing spectrum is on our own from the data, by running this modeling code. And we also can learn a bunch more. We have a lot more flexible nebular physics. We can have free ionization parameter, gas density, and free elemental abundances, or just a few in this case. Okay, so here, this is just a little movie showing Q in action, where it's varying the shape and normalization of this ionizing continuum on the left here to fit the data here on the right, a bunch of observed emission lines. Okay, so this is all open source. It's on GitHub if you want to take it for a spin. But we can predict some 130 of the brightest emission lines in the UV through the near infrared. This prediction has less than 5% uncertainty, so we're good up to signal noise of about 20. And each prediction takes something like 5 milliseconds. This is a factor of 10,000 speed up from our normal Cloudy. And so Q has been a ton of fun. We can investigate mysterious ionizing sources or marginalize over things we don't know in some cases if our data aren't very good. I'll show you a few quick examples of this. Okay, so we've run Q in this case. Galaxies in the most distant universe, where the physics are perhaps the most uncertain. So this is MOM Z14 at redshift 14.4 when the universe was 290 million years old. Yeah, sharks have been around for longer than that. This is very, very far away. And Q revealed quite a few surprises in this case. We found a very efficient ionizing source, something that is outside of our stellar grid. It's producing more ionizing photons, possibly, than any star we could have written down. So we only could have figured that out by using something like Q. And we have a surprisingly supersolar nitrogen to oxygen ratio here. This also came out of Q. And we have high gas density, something like 10 times higher than we normally model, 1,000 centimeters cubed. And so this is just an example of taking physics to an area where we don't know the assumptions very well and learning something new. Okay. Another quick example, this is a Q running on Jade Z14. This is the second most distant galaxy at redshift 14.2, one of these so-called overly UV luminous galaxies at the edge of the universe. A postdoc in my group, Dr. Jake Helton, just got a 50-hour rest optical JWST MIRI spectrum of this object, longest MIRI spectrum ever taken from Webb, and enormous investments. And so we found a bunch of surprises here as well. In contrast to the other distant object, MOM Z14, we found a very inefficient ionizing source, perhaps because of a bursty star formation activity. And now we're on the downswing here. But surprisingly, we also found something like 50% solar metallicity in the gas at the edge of the universe. From classic strong-line methods, we would have gotten something like 5% with large uncertainties. But Q takes in a lot more information, a lot more lines, including in the far IR. And in this case, we find something closer to 50%, which is a stunning number. How do you get 50% solar metallicity at this time? So we have this very massive, chemically enriched, declining star formation rate in a galaxy at redshift 14.2. This is intriguing and something we're still thinking about. Okay. One last example I'll show you. I know we're approaching the end of time, so I'll move through this quickly. But in brief, this is the decade where we're kind of taking huge ground-based spectroscopic surveys, and we're getting millions or tens of millions of spectra, some space-based, Roman and Euclid, or ground-based, PFS, DESI, and others. And so I'll talk a little bit about what we can do with spectra as well. I'll talk specifically about PFS briefly. These ground-based surveys are fun because they are huge areas on the sky. This is a couple of PFS pointings compared to the largest survey from Webb, Cosmos Webb. One pointing at PFS is substantially larger than Cosmos Webb. So this is something I'm quite invested in. I spent a lot of my time thinking about PFS, as do I think some of you in the audience. And it's going to be a fantastic survey. It's starting sometime in the fall this year. And we'll get something like 5 million spectra overall, something like hundreds of thousands of spectra at redshift 1 to 2. And we can specifically get spectra of very massive rare things with PFS. And so here's a few of the questions we're thinking about with PFS. To get everyone ready for this, we've been thinking about speeding up our modeling in a similar way. Okay, so computational challenge, we can play the same game and we can build neural net emulators. Previously, we built them for photometry. Now we're emulating spectra, plus black holes, plus cloudy emulators, plus dust, and so on. And these work beautifully. These are very fast and they scale efficiently on GPUs. So we get something like 100 times speed up if we're able to predict multiple spectra at once. So same thing. We can rapidly generate thousands of spectra at the same time. Let's try something new. I'll just show you one quick example of this, and then we'll conclude here. Hey, I mentioned earlier, bursty star formation is very, very hard to model in single objects, thanks to this outshining effect. So this is one of my former postdocs, Bingji Wang. She spent some time doing these simulations where she would generate perfect galaxies in model space with high solenoid spectroscopy and fit them perfectly. Right? And so here, this is an example of one where we have bursts. The star formation rate, the true star formation rate is the dotted line here. So it goes up and down and up and down and up and down. We generate a perfect fit, the best we can do to one object, with a perfectly spaced star formation history binning. And we get zero bursts at all, yet we fit the light to perfect precision, chi-squared of effectively zero. Okay. So these bursty star formation histories, they simply don't leave a signature in the data. It's impossible to measure them for one object. You might say, Joel, well, you're using the wrong prior. You just said priors matter, so why don't you put in a bursty prior? So we can play the same game with the bursty prior, and the bursty prior says, fine, we need one burst to describe everything. We don't need anything else. Okay? Total failure. We don't know this galaxy is bursty from looking at its SED. Okay? This is a big problem for modeling. In addition to not being able to recover the burstiness, if this is happening in the real universe, we just get the wrong answer all the time. We get the wrong star formation rate, we get the wrong mass, we get the wrong age, even if we know it's bursty. It's kind of a disaster. So this is not a solvable problem for single objects. But what we can do is model entire populations at the same time. And if we can catch a whole population of galaxies and a complete population, we can see galaxies in all phases of the bursts. And then we can actually get out the correct bursty star formation history. And so that's work led by one of my students, Emily Burnham. The paper came out just this year. And so you can generate populations of galaxies with this approach. We can show that populations have very different observables. This is not a degenerate problem for populations. And so we set it up with this model for modeling star formation histories. We use the power spectrum density approach, which is a nice family of models to do this sort of work. And we can show, if you write down the power spectrum, you can constrain the power spectrum very nicely. And another advantage of using the power spectrum is you can put all the galaxy formation simulations in a power spectrum. It works well. We talked about how hard fitting one galaxy is. Okay, but fitting many galaxies is actually pretty straightforward nowadays. In this case, we use a neural net emulator to generate populations of galaxies with different parameters. And then we use simulation-based inference to build an inference pipeline for populations of galaxies, all of them at once, fitting everything at the same time. And we can show that we get out quite good constraints on the burstiness from the whole population. Even though one galaxy, it's impossible. Okay. And this kind of thing, you can build it on a cluster. It takes a lot of time to train on the cluster. After that, you can run it in seconds on your laptop. Okay. And so this is just some of the mock results we've gotten out of this. And so here I'm showing in red, the dashed red line is a fire-like power spectrum density. Fire is a very bursty model of galaxy formation. And the dashed orange line, this is an illustrious-like power spectrum density. Illustrious is much less bursty. And we show that given something like a few hundred JWST observations, we can distinguish between these two things at very high precision. And so this is super exciting. Outshining is a problem that has plagued this field for decades. And now I think we can solve it. It is impossible for one galaxy, but by fitting many galaxies at the same time, it becomes pretty dang easy to pin down. This is an example of completely new science directions we just couldn't do 5 years ago. And so this has been a ton of fun. And so we're working on ironing out the details of this model, trying to forward model or selection function, which turns out to be very important. You need the whole population. You can't just have the bright things. And folding in fundamental stellar physics uncertainties and so on. But this has been a very active project. All right, I'm going to wrap up for you. Thanks for sticking with me here. Hey, just one moment to think about how far we've come. Time it's taken to fit a galaxy broadband SED using on-the-fly stellar population generating. In 2017, it took 100 core hours. This is when I started my postdoc. It was very slow. By 2019, I spent a lot of time in the code dungeons working on code optimization. We squeezed out a factor of 5. In 2021, we brought this down from 20 core hours to 10 core minutes using emulators. And then in 2024, we put all these things on a GPU. We got another factor of 10. Okay. And now simulation-based inference yields 0.02 GPU seconds per object. A factor of 1,000,000 speed up in something like 5 to 6 years. So hold on to your hats, folks. We can do a lot more efficient modeling than we could before. And so we just need to be able to parameterize the physics. And so I'll just leave up my conclusions here, talking about things we've sped up. Oh, let me pop that back up. Yeah. Things we've sped up and new things we've been able to do. So thank you.
Thank you. Do we have questions from the audience or online?
I have one comment maybe.
Do you hear?
Can you hear me?
Yes, I might have to ask you to clarify, but I can mostly hear.
I'll go a bit closer.
Oh, yeah.
So thank you. I really like your talk. I have one general question actually about the training of emulators. I mean, I'm just going to say something generic. For whatever model you have, there will be always this kind of space of all possible solutions. That any given neural net will try to create a map, a manifold that tries to approximate this space. At some point, you decide that the neural net is frozen, that you learn somehow the emulator. But even if you do cross-validation, you are still constrained by the training that you decided to use. So how do you control by model misspecification in the sense that eventually you may go a bit further from the distribution that you trained it? So how do you handle that in the user in sort of active inference? Just a general question for any model, it's going to face this, right? So
yeah, no, I appreciate your question. I mean, 15 years ago, if you asked me about the biggest problem in the field, I would say it's model misspecification. And so emulators do not solve that problem. In fact, if you built the best emulator possible, the best thing it could possibly do is do the exact same thing you could already do, just faster, right? It's just, you can think of it as a fancy interpolator. That's sort of all it is. So emulators do not solve model misspecification. They don't actually do anything about model misspecification. In some sense, they make the problem worse because if you generate everything on the fly, you can play with your model. But if you freeze everything into an emulator, you lose that flexibility. Okay? So I totally agree. It doesn't solve that problem. It doesn't address it. In some ways, it makes it worse because the models are less flexible. But when things become faster, you have a lot more freedom to bolt on approximations or add in extra uncertainty in regimes where you know the models aren't that good. So for example, if you think your infrared photometry is maybe plagued by physics you don't know, you can write down a custom model that says, well, let's add some extra uncertainty to the infrared, or let's learn the ways in which our infrared photometry is offset, and then add in a data-driven component to the model. And so I agree with the thrust of your question. It doesn't solve the major issue, but what it does is it gets all of the complications that we normally worry about to get our codes working, that becomes abstracted away into an emulator, and we can spend our time thinking about the real physics and building the models or understanding the residuals or doing the stuff we need in order to improve our understanding of the physics. And so that has become the goal. And so I think we can do it more efficiently now because we're not worrying about all the other stuff from the technical side. We can really zone in on the physics. And that's what we're trying to do here. I mean, if you look at this, you'll see we are using these emulators to strip away all the model misspecification that we had before. We're fitting galaxies as they are spatially. We're allowing for complete freedom in our ionizing spectrum and seeing what we can learn. And at the bottom, we're saying, well, let's fit populations of galaxies so we're not worried about outshining. That's sort of the direction I think these emulators help us go, even though the emulators themselves do nothing about model misspecification. So great question.
Thanks.
More questions? About the set fitting that he presented before? No student questions? Okay, do we have questions online? If not, let's thank Joel again. Thank you so much.
Well, thank you. It was a pleasure.